So I share the screen with you. Yeah. So we are at the ETAP simulations, right? ETAP short circuit study ETAP module, the part number 4 of the syllabus, correct? My voice and screen both are okay for all of you, right? Please let me know.
Yes, sir.
Fine, yeah. So far we have discussed the ETAP software introduction, that why we use the ETAP and other simulation software that we use in the power system, right? So that we have seen. And after that, we have discussed about the load flow analysis. And then we have discussed the short circuit current. One topic, one session on the short circuit current, just the introduction part that Venkatesh have delivered, right? Correct. So any doubts so far? Today Venkatesh is traveling, so he is not available for the class. So I will take the today tab topic, the short circuit topic. And since short circuit is very important topic, so I wanted to club both the substation and the E-tab and the industrial, both type of the electrical system together, so that you have the wider like understanding that where we go with the specifications, where we go with the grid regulations, and where we go with the ETAP study. So due to that reason, I decided that I will take the topic today for the short circuit current. So before coming to the comparing both the grid and the industrial electrical system, I'll start again from the basic, so that if anyone could not attend the study class, so they can revise. And since short circuit from their conceptual discussions, many questions comes during the interview time as well. So due to that reason, I'll start again the short circuit from the basic, from the beginning. But my agenda would be that I'll try to tell you that where you should go with the ETAP short circuit study and where you should go with the grid regulation short circuit study. If you remember, so far we have discussed short circuit study previous as well, right? In the module number 1 also,
Yes,
we have
sir.
discussed the short circuit study, right? So already in the module number 1 also we have discussed about the equipment common design parameters. So in the common electrical system design parameters for high voltage equipment from IC standard. So in the common design parameters, again, we have discussed about the voltage, insulation level, short circuit current. And then we have calculated the short circuit current for a solar power plant substation as well, right? If you remember, all of you. So
Yes,
when we will go with the design as per the grid, when we'll calculate this, and when we'll go with the ETAP. So all the concept I want to discuss at once, so that there would be clear crystal idea that what kind of the reference or what kind of this document we have to refer for the short circuit current. And since this is very important parameter, the short circuit current, and a lot of parameter decided based on the short circuit current, right? So that's the reason I'm back now. So he may be Venkatesh may be on Wednesday. So from where he left, he will again start. But I wanted to touch a brief myself as well. So again, starting from the beginning. So I will request all of you, please be active, and make a interactive session. So let us start. First of all, what is the short circuit current? I'll try to start from the beginning. What is the short circuit current? What is your understanding? What is the short circuit current? So short circuit analysis, module number, which module? This topic we are discussing under this all under the module number 90. Yeah. So what is the short circuit current? What is the short circuit? Before short circuit current selection, before doing the analysis, we should know what is the meaning of short circuit current. What is the short circuit? What is the short circuit? Since this session dedicated based on the short circuit, and this is a very important topic, short circuit current selections. So please be active. Yeah, what is the short circuit? Which circuit you will call that this is a short circuit?
maximum fault current. Whenever the fault occurs in the
system, the maximum value is called the short circuit currents.
No, I'm not talking about the short circuit current. I'm talking about the what is the short circuit. What is the short circuit? What
It is a connection between the phase to earth or phase to phase.
phase to earth, phase to ground are
Yeah.
conductive part to a non-conductive part.
Yes.
Like that we can
Yeah,
say.
conductive to conductive like that.
Yeah, like that we can say. I tried to give you the definition as per the standard, So for the short circuit uh, definitions, we can take the IC 60909. So as per the IEC 60909, I took this extract from the IC 60909 as well, and same I have written in my presentation as well. So the IC 60909 class 1.3.1 definitions. So short circuit, accidental or intentional. This is visible. I don't know whether it is visible or not visible. So the IC is telling what is the short circuit. So IC defining the short circuit that there is a accidental or intentional conductive path. It could be accidental or it could be intentional. Intentional where when we are doing any testing in the laboratory, that could be intentional as well. So accidental or intentional conductive path between two or more conductive parts forcing the electric potential difference between these conductive parts to be equal or close to zero. Equal or close to zero. The potential difference forcing equal or close to zero. So taking the same definitions I listed here, the IC 60909 class 1.3.1 defines the short circuit as an accidental or intentional conductive path between two or more conductive parts forcing electric potential difference between these conductive parts to be equal or close to zero is called a short circuit. Now, the next question comes that what would be the case when the potential difference is close to zero, and what would be the case when potential difference is equal to zero? Right here, the IC is telling two things: potential difference to be equal are close to zero. So when it would be equal to zero are close to zero. Close to zero means it is not zero, right? It is nearby zero, correct? Close to zero. So any incident, any example of the short circuit situations when it would be close to zero and when it would be equal to zero? Anyone?
Phase to ground is equal to 0, and
Yeah, come. Yeah, say again, Dennis. Say
it
again.
is a phase to ground connection is the close to 0.
Yeah, equal to zero, right?
Yeah.
Means there is a direct connection of
Connection
any light part to the ground,
ground, yeah.
right? So that would be equal to zero, the potential difference. When it would be close to zero,
Maybe between phase to phase.
no, not between face to
Through
face.
resistive path.
Yeah, means between both line to ground or between line to line, there is some resistive path coming.
Okay.
In that case, this potential difference would be close to zero. For example, there is a transmission line, right? There is a transmission line. There is a transmission line conductor. It is like running, and this transmission line conductor, due to the wind situations or anyhow, it is coming in close contact with a tree, right? Right? The any conductor coming in close contact with any branch of the tree. So what will happen? There is fault happening. The fault is happening. But since this tree branch providing a high impedance to the faulty circuit, to the path, in that case, the potential difference between line to ground will not be equal to zero, and that will be close to 0. Is it making sense? This example making sense?
Yes, sir.
Let us see. Let us see. So here we can take this circuit as an example. So when between two paths there is bolted short circuit, then it would be equal to 0. And between two paths there is resistance path, there is arcing fault happened. So in that case, that would be equal to 0. And so the potential difference between two conductive parts will be equal to 0 in the case of a bolted type fault. This is the example of the bolted type fault. Bolted type fault. Whereas for the fault having arc impedance, as we discussed, if there is some impedance, right? Having the arc impedance, the potential difference will be close to 0. An example of bolted fault is when the R, Y, and B phase conductors touch without impedance in between. Our R2Y, Y2B they are touching each other without impedance in between. And we have to note that the bolted fault does not necessarily to be three-phase fault. It can be line to line, line to ground, or triple L type fault. So any conductor touching without any impedance, that would be example of the bolted fault, and in that case the potential difference will be equal to 0. Whereas the example of fault having arc impedance is the transmission line conductor broken and falling on a tree or a rock as well. The tree or rock will provide high resistance, or it will provide an arc impedance. In that situations, the potential difference between both conductive part will not be equal to 0. That will be close to 0. Am I making sense? My effort is to decode what IEC 60909 defined in their standard. So I'm trying to explain in simple language. Am I making sense? The definitions, what is the short circuit? So I started, what is short circuit? So I took this statement and then I try to understand deep this statement. Am I clear? Is it clear what is a short circuit? Let us see in simple layman language, if we are trying to explain what is short circuit to any non-technical person, so how we can define in simple statement. So in simple words, the short circuit concept in simple words can be defined as the name suggests, a short circuit when a circuit get shorted, right? When a circuit gets shorted. This means when three or two phase accidentally meet at one common point, either involving or not involving the earth, or a single phase touches the earth, current flows from the source to the fault point through all the circuit element in between, and therefore all circuit elements must have rating, which is called as short time rating, or must have the capacity to withstand this fault current till the protective relay isolate the faulty circuit. And from the source to the fault point, the circuit has the impedance, and that impedance we express in terms of the reactance and resistance are X and R, and their ratio we call it the X/R ratio of the system. So, but again, going back in simple words, this is the one statement. This is one statement. Second, I took this short circuit in more detail. Like here we can see this is the detailed explanation. So there is two different statement. One statement for simple words, circuit gets shorted. So this is how we can say what is short circuit. And again, I took some insight of the short circuit, right? So this is how we can define what is a short circuit. When in simple way, a circuit when gets shorted, when they are running, but now they get shorted, their length cut and shorted. So we can say this is short circuit. As per IC 60909, we can define short circuit current by this statement. And this statement we understood what is the meaning when the impedance will be close to zero, when the impedance will be equal to zero. So am I clear so far? What is the short circuit? This is the first topic that we understood. What is the definition of short circuit? Am I clear with this? Am I clear with this? Second, let us see the situations. What are the major causes of the short circuit? When the short circuit occurs, what is the major causes, reasons? So there are so many reasons we can list out for the short circuit. There are so many reasons for the short circuit. We can list out a few reasons below for the short circuit current in the electrical system, such as cable damage due to cable digging below ground, overloading of the electrical system, improper laying of the cables, poor maintenance of the electrical system, wrong selection or application of the switch gear, that also contribute for the short circuit. Moisture in the insulations, fire and lightning surges, this also result in short circuit. Aging of the electrical system, that also result in short circuit. Birds sitting on live conductors, and suppose they are also coming in contact with another conductor, this will also provide the short circuit. This will also may result in short circuit. Tree branch fall on the live conductor, this is also one of the reason for the short circuit. Or switching surges coming out the equipment and equipment insulation flashover, so this also could be a reason of the short circuit. So there are so many reasons why short circuit occurs, but I try to list out few reasons for the short circuit, why short circuit happens in the system. Now let us see, why do we need to be worried about the short circuit, and what is the reason that we have to worried about, or we have to careful about the short circuit current selections. So we need to be worried about short circuit as it may damage the electrical system or equipment. If equipment or electrical system is not designed to withstand the short circuit till the protection system clears the fault, means this is not going to withstand infinite time. It is going to withstand only for 1 second or say 3 seconds max to max till the protection system clear the fault. The short circuit may result in electrodynamic and thermal stress on the equipment, and equipment may damage due to that stress. So we can say short circuit lead to undesirable current flow in the electrical system. Short circuit lead to excessive current magnitude. This may lead to equipment damage, and the short circuit magnitude may be 10 to 20 times higher than the normal current rating of the electrical system. So that is why we also have to careful about the short circuit current selections, and proper selections we have to do. This short circuit may like lead to excessive over voltage. Is it okay? Excessive over voltage, when this over voltage may come due to short circuit, when the over voltage may come. Any example?
Like
Excessive due to the short circuit may lead to over voltage. Is it
unearthed
correct?
system. In unearthed system, it will happen.
Unearthed system are the resistive earth system.
Yes,
In that
yes.
case, it may lead to excessive over voltage. Short circuit may lead to hazardous to working personnel. Short circuit also may lead to generator out of step or angular stability, and then this may lead to loss of synchronous of the generator. Let us see a deep about the excessive over voltage due to the short circuit. Means because it is quite strange, the short circuit may lead to higher current, but how it is leading to higher over voltage. And due to this higher voltage, what will happen? The equipment insulation may fail. And when the equipment insulation may fail, and then equipment again may damage. So this is like the consequence effect of the short circuit due to over voltage. and this due to that insulation may fail. So let us see when the situations when this short circuit may lead to excessive over voltage. Generally, short circuit lead to excessive or high current, but it is leading. It is also like it is providing the excessive over voltage. So let us see what could be the case in the electrical power system. So let us take one example where we have taking the power supply tapping from the grid connecting to the grid bus, and from that grid bus we are taking supply to the power transformer. Let us also, we can simulate this. We can also simulate this. And let us see. So we are taking a grid. We are taking a grid connected to the bus, and then from that bus taking a two-winding power transformer connecting to the bus which we are using for further distributions, and then taking a connecting to the load, suppose here. So suppose let us see the similar kind of relative. So here first go with the bus. Suppose this is 11 kV bus, and tapping that we are doing from the utility is 11 kV. The short circuit current from the grid 25 kiloampere. The XYR of 14. Okay. Let us take a transformer. Let us take a like 100 MV, not 100 MV. Let us take a kVA, something 1000 kVA power transformer, and then this rating primary is 11 kV, secondary let us take 0.433, and then we are going with the typical impedance. And now here it is important thing, delta and star going solid with resistance, putting some resistance value here which is 2.5 ohm nearly. Click on the OK, and this is the bus that we are taking 400.415 415 bus rating, and here we are taking some load. Let us take this load. It is just so we have taken 1000 kV, so we are taking 80% loading. So let us take 80% loading means 800 kVA load connected to the system, taking the full constant kVA load, dynamic load or motor type load. 80% power factor, right? Let us go with the 100% power factor, no issue at all. Just this is for example. Info rating is 0.433. Right. So now let us do first the load flow. Everything is fine. Now go to the short circuit. So now I'm doing the short circuit, and now running. I'll come on this later on. 60909 T23. Take this out of service. Service. So here we are taking the case. Now what we are doing, we are trying to run it, and let us show this symbol also physically. It will appear. Let us take this delta star, right? Star is over here. Now delta star is solid resistive grounding, right? This is the case now we are taking. So now running the fault current, going to the display, Now L2G, and let us see their like phase RYB. Correct? So what the incident happening here? This is 415 voltage system or 420 voltage system. This is a star. So a star means between the phase between the RY, Y2B and like V2R, what should be the voltage? What should be the voltage? Phase voltage, right? And what should be the phase voltage? What should be the
233.
voltage? So 415 divided by how much? 1.732, right? Root 3, isn't it? So 230, 240 should be the voltage, right? Correct? Let us take this. I'm going grounding, taking a star, but now going to the solid grounding. Click OK. Run again. 60909. What is 250, right? Isn't it? So I'm going with the solid grounding. Now I'm going with the solid grounding. Grounding, solid. 250 voltage coming, and this 0 kV because the fault happened here, and we are taking line to ground type fault, right? Is it fine? Now if I just change the transformer secondary winding grounding type from solid effective grounding to the resistive grounding, and then in this incident, if any fault occurred on this LV side bus, then this fault value would be more than phase voltage. It will be equal to line voltage. So taking this example, I am telling here this short circuit lead to excessive over voltage as well. Making sense? Am I making sense? Right? So short circuit can increase the healthy phase voltage. Below is an example. So if you take a transformer with ungrounded system or with a resistive grounded system that we have taken, we took a transformer with resistive grounding. And if a single line to ground fault occurs, yes, we perform single line to ground fault. So go to the display options, run here, fault type L2G, RYB, ABC, right? So perform the single line to ground fault occurs. And then at the healthy phases means fault happened on the R phase, suppose. So Y and B was the healthy phase, but on the Y and B phase, the voltage magnitude increased. The phase voltage increases from the phase voltage to the line voltage. That the statement, and that is the simulations that we can see. The phase voltage increased to the line voltage. Am I making sense? Am I making sense? Or I can do one thing if I'm not clear. So I take Control C and then move from dumpster here, put here, and then here, then here, like ungroup, click here, grounding, star, taking solid, click OK. Now you have both result in your hand, and then you can simulate 60909. All right, is it fine? Star resistive, voltage 0.2, 0.4. Am I making sense? Am I making sense? Am I able to say that fault short circuit increase the voltage as well? But there is certain situations, not everywhere, certain situations. So I took the situations that when the short circuit increase the voltage. So the short circuit not only increase the current, it may increase the voltage as well. Therefore, the fault needs to be cleared as soon as possible. In the case of EHV system, since it is connected to the generator, the extra high voltage system connected to the generator may go out of step and may lead to loss of synchronous. Therefore, in the extra high voltage system, we need to use the unit protection system, which is fast in response compared to the time graded over current protection, which is used in the voltage, medium voltage and high voltage system, right?
Yes.
Now, so what we discussed so far, what is short circuit? This we discussed. Then we discuss what is the reason of the short circuit. What is the reason of short circuit? When short circuit occurs, reason of short circuit, right? Then we discuss why we need to worry about the short circuit. Why we need to worry about the short circuit, right? That we discuss. And then we discuss that whether short circuit may lead to over voltage as well. So the reply is yes. And where it can go, so we have discussed one example as well, right? Now let us see the profile or nature of the short circuit current at the event of the fault. This is important, at the event of the fault. Why at the event of the fault? I think yesterday Venkatesh also have taken this topic, but since it is important to understand the basic concept, that's why again I am taking at the event of the fault. Why it is so? At the event of the fault, let us see. But keep in the mind, I'm discussing the nature of short circuit current just at the event of the fault. You can see after 10 milliseconds, just when the fault occurring at that moment, what should be the profile or nature of the short circuit current, right? So that we are discussing. So now we are discussing when the fault occurs, whenever short circuit or fault occurs. So what is the nature or profile the current, short circuit current, right? We know what is the nature or profile of the current, normal current. This is like this, right? The sinusoidal waveform, right? Isn't it? This is what we know when system is normal. Let us see when system is not abnormal. Then what is the profile coming? So when the short circuit occurs, the total short circuit current, or we can say the short circuit current at the just instant of the fault has two components: the AC component, the DC component. We have already discussed about the DC component, right? Why the DC component come into the electrical, into the AC power system? Because all, each and everything is AC. So from where DC comes in the picture, right? Already we have discussed this during the CT, during the breaker. If you remember, during the breaker, we discussed about the asymmetrical breaking capacity of the breaker, right? Am I audible to all of you? Like, I'm not getting.
Yes, sir.
There is.
Yes, sir.
Yes, sir. We have discussed about it.
Yeah. So let us see again all together, all the short circuit concept at once. So when the short circuit occurs, the short circuit current at instant of the fault, just instant of the fault, has two components: the AC component and the DC component. Now let us see why the DC component in the AC power system network. In the electrical power system network, most connected load are inductive load. Are you agree with my statement? The most connected
Yes,
loads are the inductive load in the nature, mostly predominant the inductive load in the nature, with a small amount of the resistance. Resistance would be, but that will be a small amount of the resistive load. These inductive loads L store the electrical energy in the power system, which is also referred as the line charging current. That already we have seen about the line charging current, right? During the module 1, isn't it?
yes, sir.
Yes.
The line charging current. So this whatever the energy they are storing, that we can refer as the half Li square. E is equals to half Li square, 1 by 2 Li square. How much energy is stored by the capacitor? How much energy capacitor is stored?
Half CV square.
Half CV square. Yeah, this is the energy that capacitor is stored. The equation of magnetic energy E stored in the inductive L can be written as half Li square. Whereas the equation for the magnetic energy stored by the capacitor can be written as the half CV square, right? Whenever a short circuit occurs, they means inductive loads. Whenever short circuit occurs, the inductive load start releasing the stored energy. This is the stored energy in a linear, because they are releasing, so they are not going to follow any sinusoidal behavior. They are just releasing. So they have they have a higher amount of the energy, but over the time period this energy will decay. So they start releasing the stored energy in a linear decaying, and this decaying is unidirectional. What I mean by unidirectional, that the direction is this direction. See, this is sinusoidal. Unidirectional means there is one direction, unidirection. Start decaying unidirectional wave, and that wave appears like a DC due to its unidirectional behavior, due to its unidirectional shape, right? So this is the reason we are telling that at the event of the short circuit current have the AC component plus the DC component in the short circuit current. Am I clear? With, even though Hari, sorry to meet you, Hari. Uh, there was noise coming from your side. Please, if you have any query, please message me. I will take up your query.
Yeah, Raghav, just one question. The capacity portion also releases energy, right? Does that contribute to the DC component?
Yeah, see, you are not connected to the capacitive load. You are connected to the inductive load, and capacitive will inject the power. I'll take this through one example as well. Okay. I hope you remember the Ferranti effect. Dev, I think you have asked me, Dev. Remember the Ferranti effect? The Ferranti effect, in that capacitive component injecting the reactive power, right?
Yes.
And this inductive, they are releasing this energy. So due to this, since it is decaying, so if we talk about the behavior, so first of all we have the AC. First of all, that is everyone know. Now I'm telling that this AC, this at the instant when the time equals to 0, when the fault just occur, so this AC plus there would be a DC component as well, that is decaying plus unidirectional. So what we are doing, we are combining both. And then we developed a short circuit waveform. So this DC that we will see, this short circuit waveform we will see just now. This DC component is unidirectional and decays exponentially. To tell in simple language, I tell it decays quickly with time. The time required to decay the DC component will depend on the system reactance R, X. How much is the X? If X is higher, more time required to decay the DC component. Will depend on the system reactance X divided by the system resistance R, which is called as X by R ratio. If your X by R ratio is higher, you require higher time to decay the DC component, right? It means your peak current would be higher. Let us see few example with different X by R ratio. I hope everyone clear about what is the meaning of X by R. This I understand.
Yes, sir.
People know what is the meaning of X by R. I will take again X by R just to quickly remind you what I mean by the X by R. So to understand the X by R ratio, time required to decay the two circuits shown in figure 1, both circuits have the same impedance, 0.4 ohm, but with different X by R ratio, 50 versus 5. So X by R ratio here 50, X by R ratio here 5, system generator, and then have this X and R. Impedance is same, but different XR ratio and different X by R ratio. Right? So if X by R ratio is higher, it is taking longer time, and total peak current is 45 ampere. If X by ratio is 5, it is just decays, and total peak current is 388 ampere just. So peak current is changing, but symmetrical current would not be changed, that would be same. The higher X by R ratio, the higher the asymmetrical peak fault current, as more time is required to decay the DC component. Let us see quickly about the X by R. This X by R, in simple words, I try to define what is X by R. So this X by R, this is the ratio of reactance. S is reactance, R is resistance. So this is the ratio of the reactance to the resistance in the current path feeding the fault. Making sense? Making sense?
Yes, sir.
The path which is feeding the fault current in that path will have some impedance, will have some resistance and reactance. So I'm telling what is X by R. I'm telling that path X and R ratio is X by R ratio. The decay of DC component depend on the X by R ratio of the circuit between the source and the fault. Higher X by R ratio means more time is required to decay DC component. Lower X by R ratio means less time is required to decay the DC component of the short circuit current. Right? This is I am telling in theoretical concept. Now, same thing you can also do in ETAP as well. Now, what I'm doing, I'm taking the same kind of the system. So bus 71 and bus 69 here I'm taking. So now what I'm doing, this here I'm taking the grid. This grid X by R I took 14. I'll come that what is the X by R ratio and how to calculate the X by R ratio, but I'm just taking a number. So if X by R ratio is 14, click OK. And here what I'm doing, X by R ratio 14. Now I'm increasing to the infinite. This value I'm increasing to infinite. Right? Click OK. Right? Click OK. Statement 2 statement. The higher X by R ratio, the higher the asymmetrical peak fault current, as more time is required to decay the DC component. Statement 1. Statement 2. Higher X by R, more time is required to decay the DC component. This is the second statement. Keep in the mind. Go to the ETAP. Now, go to the short circuit analysis. Now, I'm not taking the 60909. I will come about the IC standard, which is standard for where we have to select. There is duty, run 3-phase duty, single phase system device duty, 60909, 61363. So these all the standard IC standard that we use to perform the short circuit analysis in the ETAP. Now I'm taking the 61363. You can see their wave, right? Their wave shape, right? Means if I need to know what is the transient behavior of the short circuit current, then in those situations, we have to use 61363 IEC standard. And if I wanted to see what is the symmetrical behavior, symmetrical current, then I have to use 60909. So since I wanted to see when the fault is have occurred at that moment, what is the DC component and how much time it is taking to decay from peak to zero. So I'm going with the 61363 now, right? Taking this also, this bus as fault bus. See, Both have 26.5, 26.5, right? Now, I'm going to 6136 and plot. Here I am plotting the DC waveform. Plot type current, no. AC, no. I require DC, which bus 71, another bus is 69. 69, these two bus. Having 14, having triple like 999 bus, and click on the OK. So here bus 19 was already selected. So due to that reason, bus 19 XY are also coming. 69 and 71, they have different color. I don't know how much color you can see. 69, this color. Could you see this one? Green one. Green one have the infinite, right? XYR that we have entered. Bus 71, this one that have 14. This bus 19 might be have some different XYR. So they are taking this much time. So means here in like you can see here how much time required to decay, right? In like 4 to 5 cycles, 4 to 5 cycles, one cycle 20 millisecond, right? One cycle 20 milliseconds. So you can see here in 4 to 5 cycles, nearly 5 cycles, your DC component decays, right? But if your X by R is infinite, even though after 5 cycles, your DC component not decays. DC component still persists in the system. Am I making sense? Am I making sense? X by R 999,
Yes, sir.
50, 14, 6. Higher X by R, more time required to decay the DC component. Lower X by R, 6. Less time required to decay the DC component. Right? So am I making sense? Is it fine? X by R ratio. Now let us see how to select the X by R. Like how you will, what is the approach for the X by R selections? How we will, when we are performing the project, are performing this ETAP study, how much value we will select for the X by R in order to find out the asymmetrical current, right? For this, we need to know what is the X by R ratio that we should enter. So we have seen that at the event of short circuit, the total short circuit current has AC plus DC component. The DC occurs due to the inductive loads of the system, and in the event of fall, the current cannot change instantaneously in an inductance. Inductance oppose the change of current. Due to that reason, also like this DC unidirectional behavior coming in the AC system. Since the system mainly has the reactance and small resistance, so they can be expressed as the X by R. All the systems from the source to the fault point, all the systems could be expressed as the X by R, could be expressed in the X by R ratio. The X by R ratio is the amount of reactance X divided by the amount of resistance R in the current path feeding the fault. Below are common concept for the X by R ratio selections. Common concept. Method 1, we can take the reference of IEC 60909. The 60909 tells that generally we can select the X by R ratio as 10. So this we can use. Second method is this IEC 62271. This standard we can also refer. This standard tells for the X by R ratio selections that if we have 50 Hz system, then X by R ratio could be 14. If we have 16 Hz system, then it could be 17. This is how we can select the X by R ratio usually, generally. Otherwise, we can calculate it as well. right? So how to calculate the X-Y ratio? If you remember, these calculations we have done during the CT and then CT sizing calculations, right? The X-Y ratio calculations. I'm just trying to recall the previous discussions as well. So let us see one calculations method. How we can find out the calculations, the X by R. 10, 14, I took two value. Now we can calculate as well. So let us take one example that if in any system where you're working and the system is 220 kilovoltage system, 50 Hz is your frequency, which is important. This short circuit current rating 63 kiloampere is the short circuit current rating, and the breaker which is interrupting the circuit, and this breaker DC current breaking capacity 61%, which is given by the manufacturer. And breaker opening time is important because the when the contact separates, so like it takes some time. So at that time, this X by R, like your current is have different value. So due to this reason, breaking time is also important to use here. Then DC component of the, here we can find out like the DC component of this short circuit current, that would be percentage of the DC is equals to ISCP into E to the power minus T divided by tau. That's the exponential equation that we follow. So in order to rearrange this tau is time constant, time required to decay the DC component, it is called the tau. TP, so this tau we rewritten as TP, which is the time constant, is equals to T. Just we took the log on both side, ln on both side. So T divided by square root 2 ln percentage DC into 100. So my time required to separate the breaker contact is 40 millisecond divided by square root of 2. Percentage of the DC current at when the fault separated, breaker contact separated, our breaker DC breaking capacity that we took here 61%, and 61 into 100 just to convert percentage into the number. So this is my time constant coming 47.57 millisecond. So now this 47.5 millisecond and X by R is equals to, this X by R we can rewrite as X is equals to 2 pi FL. 2 pi FL. XL is equals to 2 pi FL. This TP is time constant, and time constant we can rewrite as L by R. So time constant 47.5 millisecond is equals to like XL 2 pi FL divided by R. So like this TP we are writing as L by R, and this L we wanted to convert into XL format. So we know that XL is equals to 2 pi FL. So 2 pi FL divided by R. So this, like in that case, the X by R ratio comes the 2 pi FL, just this value. So putting the 2 into 3.14 into frequency 50 Hz into RL, that we calculated 47.57, that let us see here as well. So 2 into pi, W10 is 50, 2 pi F into W13, which is 40 millisecond, into ln square root 2 divided by W12. W12 is breaker breaking capacity. So we are solving both equations. This as well. square root divided by W12 into 100. W12 means our breaker breaking capacity into 100. So putting all this together, and here we can get the value of x by r is equals 14.94. This is when we have the 50 Hz system. So for 14.94, that we are rewriting as 14, just using the nearby 14 of this 14.94. And if in case we are changing this 50 Hz frequency to 60 Hz frequency, just if we change this 60 Hz, and in that case the XY ratio coming 17.93, which is matching with X14 and 17. So this is the way that we can also find out, solving these equations, we can also find out the X by R if we have different breaking capacity, breaker suppression, contact suppression time. Then what should be the actual X by R? That also we can find out, or we can put in this ETAP. Whereas as per the standard, the 60909 tells to take the X by R ratio as 10. This 62227 tells to use the X by R ratio as 14 for 50 Hz system and 60 for the 70 for the 60 Hz system. But the actual X by R ratio, if we wanted to find out, we can calculate taking this formula. Percentage is equals ISCP e to the power minus t divided by tau. Tau is time constant, which we are referring as the X by R.
Yeah, one question, Raghav.
Yes, tell me.
Yeah, this X by ratio, we are like talking about the grid XR by ratio, right? X by R.
It's grid X by R. Yes.
And there is
So
X by R for transmission line and other branches also, right? Including transformers.
So this X by R that we are taking, this is for the grid, because your grid, what that you are taking, the grid will have some series reactance and some series resistance, right? And then
Yes.
you are connecting grid to a bus. So I'm calculating X by R 14 of this grid that have the series reactance and resistance. This X by R, I'm telling 14. Transformer will have different X by R. Each circuit element will have their own X by R.
So, okay, so basically the X by R seen by the bus or location of the fault.
Yeah, bus where this grid is connected.
Okay.
So this grid having the fault current, which is we are mentioning for 33 kV or 220 kV or whatever we are taking, 25 kiloampere, right? So this grid we are mentioning is that having so this we are taking a grid that suppose your grid is 33 kilovoltage having the short circuit current 25 kiloampere. So we are mentioning that this 25 kiloampere at what X by R. So that X by R 14 or 17, that are 10 that we are mentioning here. So this 14 is representing the grid X and R ratio. The grid connected to the bus, and grid, the grid is the combinations of 1,000 number of generators, the length of the transmission line. So at X by R, I'm getting this short circuit current that I'm putting here. So what happens that when we need to perform the short circuit current, so when we are taking the grid, so here in the grid we need to enter the X by R, right?
Yeah. Yes.
So that X by R I'm telling.
Yeah. Okay. Understood.
This grid short circuit current we will take from the grid. What is their short circuit current? But what the X by R? So this X by R. 14, 10, 17 based on the frequency we will enter, and then we will calculate at the event of the fault how much time required to decay the DC component. So to summarize what we discussed about the nature of short circuit current, therefore at the instant of fault, the actual short circuit current is the sum of the AC and DC component, and this DC component makes the wave same an asymmetrical waveframe that shifted up and down. The DC component is of decaying nature and left only with AC component, which is the pure symmetrical steady state in nature, which varies sinusoidally with the time, which is called a short circuit rating. So when we call short circuit rating, so we are referring the steady state current, not the this transient behavior of the current. For all the switchgear short time rating, we take the steady state sinusoidal waveform current rating. At the same time, along with this sinusoidal symmetrical short circuit current, we also specify what is their asymmetrical breaking capacity and what is their DC breaking capacity, right? So three things we specify: what is the symmetrical short circuit current, what is the asymmetrical short circuit current, and what is the DC breaking capacity. Making sense? Am I making sense? Let us see once again the nature of short circuit current, if anyone have any doubt. Even though this already Venkatesh have discussed, but I'm trying to explain like in some more deeper. So here we take this current. So this is my current on the y-axis and time on the x-axis. Now let us see when the fault occurs. Due to the DC component, your symmetrical is shifted up and down, and it becomes asymmetrical. So you can see here it is going, and on the positive side it is going, but on the negative side it is just small here, then coming down here, it is the shifted symmetrical current or asymmetrical current, we can see. Plus it has a DC component. You can see this dotted line is indicating the DC component, which will vanish after 4-5 cycles. That you can see here, 1 2 3 4 5. After 5 cycles it vanish, and after that only AC component left, only the AC component left. So here when the fault is occurring, so this 2 into IK double dash is indicating the initial symmetrical short circuit current. This is IK dash 2 So here we can find out what is the peak. IK dash is the initial symmetrical short circuit current. So we can find out at this instant what is the peak coming at this instant. Taking this 2 into IK dash, and then here after like few milliseconds, here I can see what is the peak. First IP is the first peak short circuit current. This is the first peak short circuit current. This is the maximum possible instantaneous value of the available short circuit current. Peak short circuit current, and between the peak site on the upper and the lower peak site, here we are like plotting the dot. We are connecting all the peaks by a dot, and that dot we are referring as the top envelope and the bottom envelope. So and the top peak value is expressed as the top envelope, and bottom peak value is expressed as the bottom envelope in the waveform. DC component, IDC of short circuit, this is already we have discussed. Then 2√2K IK stand for the steady state short circuit current. I double dash K initial symmetrical short circuit current. IK steady state short circuit current. Steady state. When your DC component vanished, then it steady state. So IK is symmetrical short circuit current. This is the RMS steady state short circuit current when the other component has been settled down. Right? When the other component has been settled down. So when we say this, like 25 kiloampere, 40 kiloampere, or 50 kiloampere short circuit rating. So basically, for which current we are talking? Means we are putting here 25 kiloampere. So what is this current? We have many type of the current, right? You see the I double dash K, and then we have IP, IK. So which is this current? When we
IP?
select the short time rating, so which current is expressing as short time rating?
RMS, yeah.
RMS means
Root
IP,
mean square.
P.
means which, if we see, if we look at the
IK.
waveform, if we look at the
IK.
waveform, so which current is your short time rating?
IK, sir.
IK.
Short time rating, yeah, that is the IK. IK, steady state short circuit current, and that would be symmetrical, right? So sometimes when we write the short time rating, sometimes we write a symmetrical short circuit rating, right?
Yes, sir.
Symmetrical short circuit rating. Symmetrical short circuit rating. We can also write asymmetrical short circuit rating. Asymmetrical short circuit rating means this have the AC plus your DC component as well, right? Which is your asymmetrical short circuit current. Asymmetrical short circuit. So AC plus DC. So that's coming your asymmetrical short circuit. So we are talking short circuit current, which is the IK, which is RMS current, and which is the symmetrical short circuit current when your DC component has been left. So what I'm trying to tell, that whatever the X by R ratio you select, whether 10, 20, 40, 50, 60, infinite, this will impact only on the asymmetrical short circuit current or peak short circuit current, right?
Sir.
Peak short circuit current. This will impact only on the peak short circuit current. If you're taking 10, 14, 15, 20, whatever X by R you are taking, this will have relation with the peak short circuit current. Am I making sense? This have relation with the peak short circuit current, because the peak short circuit current here, AC plus DC both component coming, right? Peak short circuit current, this have the relations. This do not have the relation with the symmetrical short circuit current, because at that moment your short circuit current has been vanished. Your DC component has been vanished. You were talking about the AC component. So whatever the short time rating we seen in day-to-day life, that is your symmetrical short circuit current. I hope I'm clear with the nature of the short circuit current and what current in day-to-day life we see. What is that current? That is your symmetrical short circuit current, right? Am I clear with the
Yes, sir.
point? So when CB breaking capacity or short time rating, when we talk about this breaker short time rating, so what rating we are going to take? So when breaking a fault current, the breaker contact will start moving apart or separating at about 50 millisecond to 90 millisecond, in this range anywhere, right? This is the breaking time that we take for the circuit breaker after fault inception, after the fault occurred. So when the fault occurring, immediately your breaker not going to isolate the circuit. When the fault occurs, suppose I'm taking the system. Here I have a circuit breaker. It is going. I have used the CT. Any fault has been occurred. CT connecting to the relay. So fault current sensed by the CT. CT gives the input to the relay. Relay have the sensing time. Relay have the sensing operating time. Relay issue the trip command to the circuit breaker. Circuit breaker have the contact separation type, right? Breaker contact separate. So there is a contact separation time. So what happening when the fault is occurred? Fault occur having this DC plus AC both like both component But what is happening when the breaker contact is separating, breaker not going to see the full peak short circuit current. It is not going to see because breaker taking like 50 millisecond time, relay also taking some operating time, and this DC vanished in 4 to 5 cycles. 4 cycles suppose I'm taking, so 4 cycles means 80 millisecond. It going to vanish, right? 50 millisecond plus relay operating time, CT sensing time. So breaker not going to see the full short circuit current. So when we specify the circuit breaker, we can specify for the short time rating, we can just specify the symmetrical short circuit current. So till that time, DC component of the short circuit is almost decayed and only the AC symmetrical component is left. Therefore, for the breaking capacity selection, for the circuit breaker breaking capacity selections, the IK symmetrical short circuit current is adequate to be selected. Along with this IK, we also specify what is the DC breaking capacity. And that would be around 10 to 12 kiloampere, not more than that. And plus we also specify what is the asymmetrical short circuit rating of the breaker. If you remember in the breaker discussions, we have discussed about the asymmetrical short circuit rating, right? Am I making this sense? I'm just trying to club all the discussions that we have discussed around the short circuit concept. So what we discussed so far? We discussed what is short circuit current. I hope everyone is clear about this, right? Clear. What are the major causes of short circuit current? I hope everyone is clear what are the major causes of short circuit current. We discussed why do we need to worry about the short circuit current. I hope everyone is clear. Profile or nature of the short circuit current. I don't know how much of you is clear or not clear. If any have any doubt, please discuss with me. If anyone have any doubt, discuss with me. Profile or nature of the short circuit current. What is the significance of the X by R ratio? That also we discuss. Am I clear with the significance of X by R ratio?
Yes, sir.
Yes, yes.
So after discussing the basic concept, let us see why the short circuit study is required in detail. The short circuit study is required. We have discussed about the basic definition of short circuit current and some technical stuff around the short circuit current behavior and nature. So now why the short circuit analysis is important? So the reason, because it is not commercially viable to construct a power system that is 100% free from short circuit or free from the fault. The short circuit occurs even in well-designed power system. Therefore, short circuit study needs to be performed in the electrical system installations. The reason to perform the short circuit study is to find out the required short circuit withstand capacity of equipment. Short circuit withstand capacity of the equipment. Are we have, right? Am I okay with this? To find out required short circuit withstand capacity, right?
Yes, sir.
Means again go to my page number 2. Here I discussed that when the fault occurs, current flow from source to the fault. When the fault occur, current flow from source to the fault point through all the circuit element in between the source and fault point, and therefore all the circuit element between the source and fault point must have the adequate short time rating, or must have the rating called as short time rating, or must have the adequate capacity to withstand this fault current till relay isolate the fault circuit. So how much current coming when the fault occurs, this we are going to calculate by the short circuit analysis. So to find out required short circuit resistant capacity of equipment, what should be the short circuit resistant capacity? Or if in case already we have selected any equipment during the tender stage, during the designing stage, now we wanted to do simulations to double sure whether that rating is adequate or not adequate. So if we have already selected the equipment short time rating, then to check and verify whether the selected short circuit rating is okay or not okay, we need to perform the short circuit study. So in simple words, we can say that the main objective of short circuit analysis is to determine the short time rating of all equipment, or to check whether the equipment short time rating used in the electrical system is adequate or not adequate. We need to perform the short circuit study. Right? And along with this, we can also have some other reason to perform the short circuit study. Since fault cannot be prevented, therefore equipment should be rated to withstand fault conditions. We need to perform short circuit study to find out short time rating of all equipment, transformer, cables, transmission line, generator, motor, switchgear, CTCB, everything, to find out the braking, making, and DC braking capacity of the breaker or interrupting equipment that I can say as the circuit breaker. To find voltage rise during the fault, that we also have seen voltage rise, to avoid unnecessary over design, to avoid the insufficient rating of equipment, to optimize the cost with various possibilities, selection of optimal transfer impedance, to provide input to relay conditions, motor starting harmonics, less transient and stability in arc plus. So for all the other power system analysis, first of all, we have to find out the short circuit study and short circuit current, that further used for all other analysis. So due to that reason also we need to perform the short circuit study. Now let us see the nature of the fault. When the fault occurs, what is the nature of the short circuit current? So the fault can be divided as series fault, shunt fault, which can further also classified as fault. It could be series, it could be shunt. Series fault could be single conductor open or two conductor open. So that is the series fault. If three conductor open, then could be three conductor open. Could be three conductor open. I'm telling fault is two types, series fault and shunt fault. And I'm telling further that in the series fault, the fault will occur when single conductor open. Or fault will occur when two conductor open. Can I write as three conductor open as well?
No, sir. Due to the three conductor open, that means no power flow.
Three conductor open
No,
means
sir.
three conductor open means you are isolated from the system.
Isolated. The conductor is isolated.
So if you are isolated, so where is the fault? There is no any fault, right? So never write three conductor open, one or two. Only in these situations the unbalance will occur. Here there is no unbalance. You are isolated from the system. Then this could be shunt fault. All you know, that's why I'm going a bit fast. Shunt fault. Shunt fault could be line to ground. Shunt fault again two types: symmetrical fault and asymmetrical fault. Symmetrical fault three-phase fault. Three-phase to ground fault comes symmetrical fault, and symmetrical fault line to ground, line to line, line to line to ground fault. It comes under the asymmetrical fault. This is all you know during the college time as well. So now series fault already we have seen. For example, a transmission line conductor is broken but does not touch the earth, so it may count under a series fault. In this case, fault only one conductor disconnected or two conductor disconnected is considered as a fault, not all the three conductor disconnections. When all three conductors are disconnected, it means there is no connection from supply and there is no unbalance occurring. So in series, three conductor broken is not considered as a fault. What is the effect of series fault? Is increase the voltage and frequency and fall in current in the faulted phase and also provide the large negative sequence component. Shunt fault effect increase the current and fall in the voltage and frequency, thermal energy, equipment damage, or voltage rise in healthy phase with lead damage to insulations. This disturbance in the control aluminum system, endanger to working personnel, generator out of stability or anchor stability. These are the effect when the fault is occurring. Now, what could be the magnitude of the fault current based on the locations where fault is occurring? So here I am the source, here I am the load. So between the source and load, there is like resistance and reactance. Like here I have indicated resistance only. So 1 ohm 1 ohm, and like here fault 1, 2, 3, and 4. So fault would be higher near to the source. If fault occurring near to the source, then it would be higher because of the low impedance. Because of the low impedance, fault current will be lower at the near to the load. If fault occur here, so that would be lower because due to the higher series impedance. Most severe fault is triple L type fault 90%, because sometimes L2G fault higher than triple L2 fault. This is the reason I'm putting here 90%, not the 100%. Only 10% other fault. Single line terminal faults, it would be higher.
Sorry, sir. This is not a right thing here, sir. Because normally the line to ground is the like 90-80%, no, sir. Why triple
I'm
line
telling,
is fault?
I'm telling which fault magnitude is higher. I'm not telling which type of fault higher. Yes,
Okay,
you
okay,
are correct. You are correct with respect that what is which fault occur mostly. So line to ground fault occurs mostly, like 80-90%.
Yeah,
okay,
it's
sir.
I'm telling which, if the fault occurs, so at which incident the current will come higher.
Okay, sir, understand.
So in the
Sir.
triple L type fault, the fault current will come higher 90% cases, and 10% cases if the single line to ground will also comes higher magnitude. The case where generator in fault near to the generator terminal solid grounded, in that case single line to ground fault would be more than triple line to ground fault. Single line to ground fault will be higher when the transfer delta star and solid grounded. In that case also the single line to ground fault would be higher. Means you can see that this as well here. Close putting the short circuit as so delta star. So L2G, take the three-phase fault which is coming 6.9 26.5 kilo ampere. I'll come and detail about this. Now I'm going with 60909, right, and go to L2G fault 31.27 kilo ampere. This is L2G fault, three-phase fault 26. Could you see the difference?
Clear,
Right?
sir. Yeah.
So here the three-phase fault 26, single phase fault is 31. So in 10% time, the line to ground fault could be higher than triple line L type fault, the transfer delta star and solid grounded system. Same with the generator channel solid grounded. Okay, so I discussed about the basics so far about the short circuit. Now I'm coming on my main objective about the short circuit current rating selection, which due to that reason I started my I took the 2 sessions, but I wanted to go with some basic concept. So now magnitude of fault current or short circuit current for the electrical power system network. So I'm going with the grid system network, the substations that we are discussing, that we have discussed so far. So short circuit current value for the grid power system. What you will do if you're working for any substations? What would be your approach for the short circuit current selections? Any idea? Any idea? What we discussed, that is the basic concept. What is short circuit? Why short circuit? Nature of short circuit. What the short circuit rating we select, we see that short circuit rating is the symmetrical short circuit rating, what we are discussing, 25, 40 kiloampere, 31.5 kiloampere. Now, how you will select, what would be your approach for the short circuit current rating? Short circuit current rating. Short circuit current rating. So we should know what type of the project on which we are working. So widely we can like divide the type of the electrical project as we are working on a grid system, grid power system, or power grid system, anything, power grid system, right? What could be the second? What could be the second?
Standalone system.
This standalone system. Means I took a network. I took a network here. Any other network I have? I can take that one. Yeah, let us take this. The grid. So I have the power plant generations. It is connected to the transmission substations. Then from here we are taking supply 11 kV and going to the industrial, commercial, or urban end users, taking supply going to the residential end users. So if we are working anywhere in this dotted line, could you see this dotted line? This one?
Yes, sir.
Anywhere, right? Means we are working anywhere in the grid. We are on 400 by 220 kV substations. We are on 220 by 66 kV substations. We are anywhere on 60 by 11 kV substation as well here. Anywhere between the grid. So the electrical system could be any power grid system, or it could be any industrial electrical system, right? Any standalone industrial system. Am I making the sense? Actually, for this reason, I took the session today. So please be active. There could be power grid system or any industrial electrical system, right? And this power grid system, again, we can divide into two parts. One, we are in the grid. We are part of the grid. Or there is a grid from where there is a grid. There is a grid from where we are tapping, or we are taking, or we are injecting power. Means what I'm trying to say, that there is a solar or wind power plant, which is producing the power and which is injecting power to the grid, and there is a transmission line through that they are connected with the grid, right? So this grid we can further divide like this. Grid system, the type of project, I'm like, my approach
Sir,
is the type of the electrical project. In that way, I'm classifying all this discussion. Making sense? This is general things. Please come tell
Yes,
you.
sir.
Is the input only solar, and this is considered if it is a normal power generation, it's also be considered. No?
Yeah, yes, that also be considered in thermal power plant, right? So when we work for any grid power system network, in that case, grid power system network, in that case, grid power system means whether we are working for any grid substations, means there is a project by the PGCIL, there is a project by any utility like UPPCL, any utility MSHTCL, any utility that have released the project in the market. You are working anywhere in the grid, right? Anywhere in the grid, power grid. I'm combining both. In that, when we work for any grid power system network, in that case, we follow the tender technical specifications, our grid specifications, our grid regulation, like CEA in India that regulate have the grid publish the grid regulations. So in that case, for the short circuit current value, we will follow the tender technical for the equipment. We will follow the tender technical specifications. For the equipment short circuit rating, we will follow the tender technical specifications, our grid specifications, our grid regulations for the short circuit current value. Reason, as the grid company that is managing the whole grid knows the entire system, knows how many thousands of generator, knows how many kilometer circuit is the transmission line. They know the entire system, and they also have the future planning. They also know the future grid expansion in coming 40 years, 35 years. So the present short circuit current is considering the future load growth and short circuit future load growth and the future short circuit capacity as well. So as we are not going to replace the equipment in future when the short circuit current increased, so in that case, when we are working for any grid substations, we will follow as per the grid tender technical specifications. In older substations where short circuit current have been increased, now we are using the current limiting reactors to reduce the short circuit current level in those substations. So this is in older substations we are doing because we cannot replace all equipment all switchgear over there. So we are putting one current limiting reactor and we are reducing the short circuit current. But when we are designing any equipment, any substations now, so we will take into the considerations what would be the short circuit current after the 40 years. So because we are not going to replace the equipment, so we'll follow simply, and we are not aware about the entire system and future grid expansion planning as well. So we will follow simply the grid regulations for the short circuit current. This is my statement number 1. Am I clear with my statement number 1? Statement 1.
Yes.
Second statement, this is about the short circuit current, but what about the normal current, continuous current? What we will do, whether we'll calculate or which document we will refer for the normal continuous current. Same concept for the, as we have discussed. Again, because we are not going to replace the equipment after 14 years, 10 years, 20 years, 30 years down the line when the short circuit current and normal current keep increasing. So we have to take care what would be the current after 35 years, 45 years, and the equipment life generally designed for that much period, and equipment should withstand that normal current and short circuit current. So same concept for the normal current as well. And for the normal current and short continuous current rating, we also follow the same concept. This is for the grid substations purely. Now coming to the solar or wind substations. So what we do there in solar or wind substations, we follow the same concept for the short circuit current and normal current. Please focus here, because when you prepare the SLT, this knowledge will help you. So for the solar or wind substations, we follow the same concept. Means I'm going to follow the grid regulations. Whereas the normal for the short circuit current, we follow the same concept for the short circuit current. Means what I'm trying to tell, you are making a 220 kV substations. At the 220 kV, what should be your short circuit rating? How you will decide? You will take based on the short circuit current at 220 kV grid voltage, right? Which is 40 or 50 kiloampere, correct?
Yes, sir. Yes, sir.
So are making a substation 220 kV. No need to calculate short circuit current. Go and take 40 kiloampere for the equipment, at least for the equipment. You are getting my point, what I'm trying to tell. For
Yes.
your breaker, isolator, CT, all equipment that you are using, their short circuit current take as per the grid voltage level. When it comes to the normal current, what the normal current you want, you will take. The normal current, yes, you can take as per the grid. This is also okay. But if you want to optimize and you wanted to reduce the normal current rating, then you can do a coordination between the voltage and short circuit current. Whereas the normal current selection shall be done according to the coordination between the voltage and the short circuit current. If you all remember this, we have discussed during the breaker, right? The coordination, the IC publication 56. Please tell no at least. If not, as so, no will also tell. Means take the IC publication 56 or the manual, and take the breaker manual. Take whatever the voltage where you are working. Take what is the short circuit current at that voltage based on the grid, 40 kiloampere for 1 second. And between the coordinations, I will take the normal current. That could be 1600 ampere or whatever required that I will take. Do not calculate the current. What I'm trying to tell means you are having a solar power plant. Suppose you are having a solar power plant, solar inverter transformer connecting to a power transformer, and then you are stepping power transformer, this taking 33 kV, step up to 220 kV. This 220 kV you are transmitting to the grid substation GSS in your grid substations. So now here you have 220 kV side of the line. So all the equipment that is coming on the 220 kV, all the equipment that is coming over here, there's voltage, which is 220 kV. Their short time circuit, which that would be as per the grid, which is 40 kiloampere or 50 kiloampere, right? So continuous current, suppose you have it, you are injecting 300 megawatt power. So you are taking 300 MVA. So but how you will do? We will calculate by the current, like V is equals to, the power equals to √3 into V I. So I would be power, which is 300 MVA, right, divided by the voltage, which is 1.732 into voltage, which is 220 kV. So you will get one current here, right now. But I'm telling, do not take this current. 300 into 1000 divided by 1.732 divided by 220, 787, right? Correct, huh? I'm not getting the response, so I'm losing my energy as well. And
Yes.
to be honest,
Yes.
to be honest, if you all thinking that why I not took the ETAP system, this is the reason, because I need the response, and this is the reason for the live class. You are there, I'm hearing, and we are discussing the concept. So due to that reason, I asked Venkatesh that you deliver the session. Because if I deliver, I need it to both side communications. Yeah.
Okay, sir.
So
we will do this.
So I'm telling, do not take 800, 787. What you will take then? Do the coordinations. Do the coordinations. Coordination. For the coordinations, you can take the IC publication 56, or you can take the manufacturer manual and take what is the voltage, what is the current, and corresponding what is the normal current available. And that would be your breaker rating, another breaker rating, discrete rating, not the CT rating. CT rating, not. CT rating would be equal to this much into 10% margin you can take. CT rating as per this, your how much current you are transmitting, how much current you are sending. CT rating would be as per this, but your breaker rating, your disconnector rating would be as per this. Breaker rate, CT rating would be as per this. Short circuit rating as per the grid short circuit level, which is given by the regulations. We will see the snapshot as well. So each country has a different grid network, so have a different normal and short circuit capacity. Below is an extract from the grid specifications for India and the UK for comparison purpose as well as. Means, because I told here each country different grid network, so I took two countries so that I can compare both their normal current and short circuit current. So first I took the Indian grid specifications, grid regulations. So when we do for the substations, grid substation in India, so what the normal current, what the short circuit current we take? Why normal current they are defining? Because they are taking the future for load growth after 40 years. What could be the growth? So from the same switchgear, same equipment, they are going to transmit the power, right? And if you see any like grid substation, if you see any grid substations, they do not go the current as per the calculations, the grid substations, they go current as per this as well. Making sense? They go current grid substation, they go CT as per this as well. But this is for the CT for the grid substation. But when you're working for any solar or wind substations, your generation capacity is 300 megawatt, which is fixed. 300 megawatt, your generation capacity is fixed. Your capacity is fixed, how much power you are going to generate. So you are not going to expand after 35 years. So your CT would be same. But in the grid substations where they are expanding, in that case, they do not go CT this. For anyone can tell me what the CT rating that they take? For 400 kV, what the CT rating that they take?
31/0.
3000, right? For 400 kV, 3000. For 220 kV,
2000.
2000 dash 1000, right? No?
Okay.
And due to that reason, they are taking the multi ratio CT, right? Multi ratio CT.
Yes.
So that
MRCT, we are using MRCTs.
yeah. Anyway, so normal current 765 kV substation working, you take this current. 400 kV, they take this current. 220 kV, you can take any of this current. 132, take this current. 66, taking this current, right? Short circuit current. 66, 31.5. 132, 31 or 40, and you can take. 220, 40 or 40, 50, any you can take. 400 kV, 50 or 63, you can take. Now see, they are also increasing. Earlier they have 40, now they are coming 50. Means the grid is also revising their short circuit ratings. 400 kV, 50 or 63. 765 kV, 40 or 50. 1150, 50 kilometers per 1 second. So this is the short circuit current rating that you will directly select for your substation equipment without doing any ETAP study. Am I clear with this statement?
Yes.
This is for the Indian grid system for the substations. Now, I'm taking the same for the UK. My statement that each country have different grid network. So I took the Indian, now I'm taking the Indian grid network, now I'm taking the UK, their grid network and their short circuit and normal current rating. So for I have took all the voltage level here. Here I took all the transmission voltage, but here I took all the distributions and transmission voltage both. The 33 kV, 11 kV is considered as distribution voltage, not the transmission voltage. So this is the transmission voltage, continuous current and short circuit current. So now if I take this one, having the distribution voltage plus transmission voltage. So through this slide, you also can see that what is the voltage range available in the UK for the distribution and as well as the transmission. The highest voltage is 400 kV. In India, the highest voltage is 1150 kV. Why there is different? Why they don't have this 1150 and 765 kV voltage? Because their geographical area is small. UK is very small country compared to the India, right? So when your geographical region is small, you have lower number of transmission voltage. When the geographical region is large, then you have mini and transmission voltage, and you have higher transmission voltage because you need to send power for longer overhead line, for longer line, transmission line. So you require higher voltage. Here their country is small, so they do not need to send power for the very long length. So they manage with the smaller voltage range as well. So 6.6 kV, 11 kV, 25 kV, 33 kV, 132 kV. This is the voltage current rating that they take. 220 kV, 275 kV. They have one intermediate voltage which is 275 kV. In India, we don't have this voltage. 400 kV, which is maximum normal current is 4000 ampere. You can see 400 kV, 3150 ampere only they are taking, but they are taking larger current. Come about the short circuit current. So normal system voltage, single phase short circuit current, 3-phase short circuit current, duration of short circuit current, and DC time constant. See, these countries are very systematic about the regulations, about the grid managing. They will provide each and every data whenever any company working for their project. You can see here, we don't have information about the single phase short circuit current. We don't have any information about the DC time constant, but here we have all the informations. The single phase short circuit current, 3-phase short circuit current, and DC time constant. What is the meaning of DC time constant? What is the meaning of DC time constant? 60 millisecond, 60 millisecond, 60 millisecond, 90 millisecond, 45, 135, 60, 60. DC time constant means same. The DC time constant means the DC component decays according to the time constant. Means the time required to decay the DC component. Yes. So they are also specifying that in 60 millisecond, in 60 millisecond, in 60 millisecond, 60 millisecond, in 90 millisecond, your DC component will decay. They are also specifying. So based on that, switchgear need to be manufactured. Short circuit rating 400 kV, single phase short circuit 55, 3-phase short circuit 50 kiloampere. 1 second. 275 40 40, 220 40 31.5, 3-phase 31.5, single phase 40, 132 kV 25 and 20 kiloampere just. Whereas 132 kV is 31 or 40 kiloamperes. So here drastically change. 25 15, 3-phase not applicable. 33 4.2 17.5, 11 13.1 13.1, 66 13.1 say 13.1 kiloampere. So short circuit different here. So when you're working for grid subsystems, go with this regulation, this slide, and take short circuit current for your project. Whereas when you are working, not working for, so I'm clear with this part. Short circuit current selection.
I have a doubt, sir.
About the power grid system.
Hello?
Yeah.
Sir, I have a doubt. This whether it will depend on the frequency system, 60 hertz and 50 hertz.
That may be means I'm not 100% sure, but I can guess that may depend. And since UK and India both have 50 hertz frequency system. US have 60 hertz frequency system.
Yeah, in Saudi also that is in 60 hertz system.
Yeah, few part, not all, few.
Not all. That way, if 60 hertz system and 50 hertz system is connected together, if it will be a problem, no?
Yeah. Yeah, Abhijit, anyone have any query regarding the short circuit current selection concept approach for the?
Hello.
Yeah.
Only when we are going to consider the solar power plant, we have to calculate the because of the CT selection, we have to calculate the current rating, right?
I'm coming on that. Yeah, I'll come in. This is my next slide. Sir?
Yes, sir. Yes.
This is
Continue.
Yeah, this on this topic I'm just coming. So when working for grid substations, we will follow grid substations. Power grid, PGCIL, UPPCIL, PMSETCL, any utility, state utility grid substations. We will follow the grid substations. We will follow the tender technical specifications, grid specifications for the normal and short circuit current both ratings lists. Now, coming to the solar and wind substations. So when we working for solar and wind substations, we will follow grid specification for the short circuit current label, statement number 1. And based on the coordination between the voltage and short circuit current, we will select the normal current rating, statement number 2. Now, third statement. However, sometimes for few calculations, such as CT sizing calculations, earthing calculations, relay setting calculations, sometimes in these calculations, when sizing comes very high, taking the full grid short circuit current 40 or 50 kiloampere, sizing is very high at grid short circuit current. So to optimize the calculations, we can calculate the short circuit current at the solar or wind plant end. Okay, Saurabh?
Yes.
And
Yes.
that value we can use for the calculation.
Okay, I got it.
But for the equipment rating, except CT, for the breaker, for the isolator, for the these equipment rating, we will be based on the grid short circuit rating, as the type test report is not available on so many short circuit current. Because every
One doubt. What
every
about
plant, every plant will have different transmission line length. Every plant have different conductors like zebra, panther, moose, right?
Yes, sir.
So at the plant in different current will come. So for the CT earthing relay, you calculate the short circuit current contributed by the grid to your plant. Okay.
Okay.
But for the breaker, do not calculate the fault current contributed by grid to your solar plant, because if you will not get the breaker, you will not get the isolator, because breaker isolator is type tested based on the grid short circuit current. So whether your short circuit is 10 kiloampere, but you have to use breaker at 40 kiloampere.
Because of the
Type test limitations. Each manufacturer not going to
so we
manufacture
have
the
to follow
breaker.
the grid regulation.
Yeah.
So we have to grid regulation for the query customer from which we are getting the.
Sorry, your voice is very low and breaking as well. Could you again?
Okay. So I am telling that except the city, we have to follow the grid regulation, right?
Say again. Say again.
Except we have to follow the grid regulation, right?
Yeah. Except the CT equipment, except the CT equipment, for other equipment, follow the grid regulation. Okay.
Yeah. Yes, sir.
But in CT you will also follow the grid regulations. But I am telling, sometimes when we calculate the knee point voltage,
Yes, sir.
at the time of the knee point voltage only, you have this choice that you can calculate the short circuit current at the plant, and that short circuit current you can use in the knee point voltage calculations. But when it comes to the CT short time rating, that would be as per the grid only, 40 or 50 kiloampere. But CT knee point voltage, if coming high at grid short circuit current, then you can recalculate by actual short circuit current, which is injected by the grid.
Okay. Okay. Okay, I got it.
Yeah. So if anyone having any query, let me tell me, please. Discuss me, yeah, because see, we are very close. We are very near to finish the this training program. So might be you and me both. I don't know when we are going to connect with each other. This is the opportunity. Equipment, if I have any rating like CT instrument transformer, yeah. So I take this instrument 220 kV CT secondary nameplate, GA drawing. I nameplate now. I require that. Here, let us see. Rated short time current 40 kilometer, right?
Yes, sir.
So for the CT, 40 kiloampere rated short time rating. But when you calculate the knee point voltage, here you put the short circuit current as well, right? IF, I put ISC, you put, right now. We have seen.
Yes.
We have
900 volt.
Yeah. So when we calculate the knee point voltage, then again In the knee point voltage, again we take short circuit current. So that short circuit current you can
Calculate.
calculate. See these calculations. See these calculations. Utility here.
Yes, we have done that.
Yeah, you have done this utility, taking the ASSR zebra line taking, and putting the zebra line 15 kilometer length, zebra line resistance X and R value, okay, and zebra, and then converted all kV and MVA into the per unit system. So per unit MVA based by MVA fault, per unit of the utility we calculated, per unit of the transmission line again we calculated this formula we discussed, right?
Yes,
And
sir.
then this utility transmission line connecting to the 220 kV bus. So at 220 kV bus, we calculate the fault current which is coming 13 kiloampere, right?
Yes, sir.
Then transformer 220 33 kV. Then here again we are calculating the fault current.
Fault current.
About 12 kiloampere, right? Then it
Yes,
is
sir.
going and it is connecting with help of the cable. It is connected to the inverter duty transformer.
Inverter duty transformer.
Then again it is going to the different inverters. So this method we have discussed in module number 1. So when it comes to the knee point voltage, when it comes to the relay coordinations, when it comes to the earthing calculations, so sometimes first you go with the full fault current, but if you see that knee point voltage is coming very much high,
yeah,
in the earthing calculations conductor sizing coming very much high, so recalculate and now calculate the short circuit current at the plant end, because at the plant mostly the short circuit current is injected by the grid, but grid connected with a transmission line. So transmission line going to reduce this fault current at the plant end. 40 kiloampere I'm taking full, but I'm getting just 13 kiloampere, right?
Yes,
so
sir.
I can take 13 kiloampere, and based on that I will do relay settings and I will do the CT calculations. Sometimes I also use these things I have done for my earthing calculations as well. So I need to perform the earthing calculations for the similar kind of solar substations. So I have 220 kV. So when I took the 40 full fault current, then the earthing conductor size GPR, mostly I was struggling with the GPR and coming very much high. I'm not able to meet out the touch and step potential criteria. So what I done here, instead of taking 40 kiloampere, I took just 15 kiloampere. Symmetrical system at fault current.
Okay.
Right. And then I
Yes, sir.
calculated, then I again calculated all the earthing. Then I again calculated all that thing, taking the 15 kiloampere just. So the clarifications why I took 15 kiloampere, why not took 40 kiloampere? Because 40 kiloampere is grid short circuit rating. At the grid, I am connecting a transmission line which is having the impedance, which is reducing the short circuit current at my solar plant. So that at the event of the fault, this current will inject into the grid. So to optimize, I took that current.
Okay, sir. Yes, sir.
This is solar and wind. But if you are in the grid, if you are in the utility, then don't do this. Go with the full 40-50 kiloampere. Okay. If not matching, then do other
then I have to follow the necessary calculations. Okay.
Then follow the IEEE and then see what is the method to optimize.
But first I have to refer the grid code.
Yeah. So when working with the grid, you will directly go with the grid short circuit current. When working with the solar, first go with the grid short circuit current. But sometimes in the calculations, if taking the grid short circuit current, you are not able to meet, or it is the calculated knee point voltage of the CT and earthing is not meet out, is coming very much high, then re-modify and take the actual short circuit current which is injected by the grid to your end. Source is grid, right? At the solar substance, what is at the solar substance you have grid, then you have solar substations, and then you have the inverter, right? So inverter is a source, and grid is
Yes,
the
sir.
source. Grid is a source. There is no any source here. Inverter is a power electronics device, which is very weak source. Okay. So who is the main source? Main source of the fault is
Grid is
grid.
the main source.
You are putting a transmission line that have resistance, that have reactance. So you are getting some fault current here. So that current I'm going to use now for all the earthing and CT calibration. But for the equipment, since there is limitations, equipment manufacturer not manufactured equipment of different short circuit rating. They manufacture single equipment based on the grid short circuit rating. So every solar and wind substance have to use their that equipment only, and which is good. You are getting 15 kiloampere, you are using 40 kiloampere equipment. So with the equipment point of view, you will also see that. But on the CT, coming back on the CT, your rating short time rating would be 40. Okay, this all with the knee point voltage. Okay, sir.
Yes, sir.
Anyone have any query regarding this? Please discuss with me. This is a short time rating selection is a very critically important parameter. Now, second, if I have a industrial system, in that case, what we do? In the industrial electrical system, where we have an incomer from incomer source from the nearby distribution substation, right? So, like here we can see that grid here.
Sir, I have a doubt. This when we are modifying a substation, existing substation, we are adding some loads extra. Whether and this is an old system, so how it will be impacted on the short circuit?
I'll come. No, for just hold on. I'll come on you. Just wait a moment. So now, so here we discuss about the grid. Now, suppose I'm a industrial or commercial user, industrial user. So here is a distribution substations. From that, I'm taking the tapping of 33 kV or 11 kV, and that I'm taking here. I will have a transformer. So that 33 kV or 11 kV will feed to the transformer. Transformer will step down to the 400 voltage or any other desired voltage, and that further will distribute all the industrial or commercial loads. So in that situations, when we have a industrial system, when we are working for that kind of electrical project, in that industrial electrical system where we have an incomer from the nearby distribution substations connected to the transformer, like here incomer connected to the transformer, or that also we can see incomer. So the incomer we represent as a grid. Incomer which is connecting to the transformer, we represent to the grid. But grid will direct not connect here. There would be a imaginary bus. So that bus we indicate like this. Means you're getting my point. Like here I'm. So this incomer we represent by this power grid. This, and then what we do, this grid rating we define that what voltage we are taking. Then what is the grid short circuit rating? We define that what is grid short circuit rating. Then we define this short circuit rating at one grid connecting to the bus. So what is grid XYR? That also we put here, right? And then we see how much grid is contributing the current that we calculate. Since if this grid connecting to the transformer, so if we connect the grid right to the transformer, one node will come here. So this node like we represent by this bus. So here either you can go like this or you can go like this. First take the grid, terminate on the bus, then take the bus, connect to the transformer, or you can go like this as well. Then to the transformer HV side, and this transformer step down to for the further distributions to the till the end load. So in that kind of electrical system, for the short circuit current value, we mostly calculate based on the contribution from the source. What is source contributing? And load contribution using an Excel sheet manual calculations are using the ETAP software. ETAP software performs the calculations by using the electrical standard. Mostly the IC 60909 we refer in like Indian RICN. So mostly the 60909 is used. The ETAP is using all the formula which is defined in the 60909, and that formula they are performing. Instead we perform manually, they perform. This software perform is used for the calculations. The 60909 is an international standard first published in 1989, which guide the manual calculations for short circuit current in the three-phase AC system. To determine the fault current at any point on the system, what we do in the ETAP when we do the project, we take the single line diagram of that industrial electrical distributions, and that single line diagram we develop in the ETAP, just taking that single line diagram, and to determine the fault current at any point on the system, prepare a single line diagram for the system indicating the source. This source could be grid, this source could be local, their generator, industrial generator or DG or some what generator they are using, indicating the transformer, indicating the lines. If grid, then there would be line as well. All other connected load as well. All load means what is the motor load, what is VOT, all the load connected. And the point at which the fault level is required, we can just take that, whether we require fault at this level, whether we require fault at this level. This level fault would be your bus fault. This fault would be your bus fault, because grid fault. And this bus we called as a grid bus. This bus we called as the 27, which is 27. This bus we called as the grid bus. So grid, whatever the fault we have specified, that fault will come here. 25 we have specified here. So 25 coming here as well. Contribution by the grid, and this much contribution by the load to here. So we can know the this bus short circuit rating, we can know this bus short circuit rating, we can know this circuit element short circuit rating, we can know this circuit element short circuit rating as well. So we develop single line diagram. What I discuss here, we develop single line diagram indicating all the source, transformer, lines, all connected load, and then we perform the short circuit current calculations. We can do by access it manually, and we can perform by the ETAP as well. Am I clear so far? Am I clear? So for this industrial system, you are going to take the ETAP in your calculations, and you're performing the short circuit.
Yes, sir.
Yeah, any doubt regarding the approach of the short circuit current calculations? Grid, industrial system, you go with the ETAP. So whatever we are discussing now on the ETAP, that is basically for any industrial system. Okay, grid we discussed now, and industrial system will discuss whether if Venkat is available, he will take on Wednesday. If he is not available, then I will take. Okay, now there is one question. What we do, just in the industrial electrical system, there would be so many loads, right? There will be like 100 number of the motors. There are so many lighting loads, heaters load. So whether we need to indicate all the loads?
No,
sir. Static and the
lump load we can march.
Yeah. So how we do? For this, we have a option in the ETAP, and this option called as the static or lump load, and this option called as the lump load. So if you see here we have lump load, here we have this induction motor load. So I can take the motor by this, and here I have the lump load. So what we will do, what we will do, if we have the large rating motor, say 500 kilowatt, 1000 kilowatt, 300 kilowatt, so that motor individually will connect. That motor individually we will connect, and we will define what is the motor rating. But suppose we have 10 HP motor, 5 HP motor, 1 HP motor, we have lighting load, we have other heater load. So no need to indicate all the loads. You do what we can do. We have a very good option which is called as a lump load. Means in the lump load, we can lump all load together, and that load we can put here. So all the load add together, and that load we will put here. And here we have the choice. What is the load type? Constant kV means your motor is constant kV, constant power. Motor is constant power load. Here I have the choice that how much is motorized load and how much is the constant impedance load. Constant impedance load means static load. The static load do not contribute in the fault current. So here I have the choice, and I can fix that how much motorized load and how much the constant load. This percentage we can fix by the slider. Okay, so no need to add all the load in your, indicate all the load in your SLD. Largest motor just indicate, other motor club and just so like a lamp load, and this percentage based on motor plus other load, you can display select the percentage here. So now whether all loads should be taken during the short circuit calculations? Answer is no. The only rotating plant equipment connected to the system, rotating plant equipment means generator, motor, these are rotating equipment connected to the system should be taken for the short circuit calculations. Actually, they contribute the short circuit current. Static loads does not contribute to the fault or short circuit current.
Sir, this inverter, if we have in the bus large capacity inverters, which are considered as static load?
I'll come on the inverter separately. You are talking about the solar inverter or like?
Yeah, large capacity.
I'll try to come on this separately.
Okay. In bus system we are using.
I'll try to come because we do the inverter modeling as well.
Okay.
We have the choice, we can do the inverter modeling as well.
And sir, what about the transformer?
What about the
Transformer?
transformer?
Transformers are also static equipment.
Transformer is static load, but since they are changing the voltage level, so due to that reason, when voltage level is changing, your short circuit current going to change, and transformer have the impedance. So impedance reduce your short circuit current. So due to that reason, transformer you have to consider whether they are not injecting, but they are contributing. Means how they are contributing, they are changing the voltage. So due to that reason, your short circuit current change. They have the impedance. So due to that also they are short circuit current change. So transfer you have to take sorrow.
Okay.
Yeah. Static equipment, I mean by the heaters, the lighting lamp. I'm telling that kind of the load no need to take. They do not. MOV, the motorized operating valve, MOV. Okay, so they are not contribute the fault. I will try to model. Otherwise, I think Venkatesh will do. They will take different load, and then they model, and then they will see how much the contribution is coming.
Okay, sir. Okay.
Either Venkatesh will take, otherwise, if not, I'll try to take. So static load does not contribute to the fault current or short circuit current. No need to take. Rotating load contribute. Take that load. Now there is again one choice here, that large motor you take, but other small motors no take, club together and use as a lump load. So all your static load and small motorized load lump together and use as a lump load. Okay.
Hi, one question. If we like clubbing the small motors, what should be the effective power factor we should be considering for that?
This power factor you are telling?
Yes. So like there are different motors have different power factors, right? So we
Yeah.
should be taking some
Yeah,
weighted average or something.
yeah, average we can take, and generally most of the time 80-85% power factor we take for the motors. So that we can put here.
Okay.
Average, otherwise average power factor we can take. And second question, when the single line to ground fault greater than three-phase fault, I think this already we have seen. This already grounded to start side of delta. This already we have seen, right? Yeah. So now coming to the E-tap short circuit analysis. So as we discussed that short circuit, the E-tap follow the standard 60909. So let us see some in detail about that. So below the reference standard to perform short circuit current calculations by the E-tap or by manually as well. IC 60909, 609 short circuit.
এবার ফেলবি ভাঙবি
Please mute. Yeah. So 60909 short circuit for three-phase system. IEC 61363 short circuit current produced for a three-phase AC isolated system. So there is two IC 60909, 61363. There is one IEEE also we can use, NC IEEE 551, which is recommended practice for the calculating short circuit current for industrial and commercial power system. Now we can see here under the IC there is two standards, 60909 and 61363. Same we can see here if we go to the E-tab, click to the short circuit analysis. So this I'm taking service out. So when I click on short circuit analysis, I can see 60909 and 61363. So let us see what the difference between both. So the IC 60909 is the steady state analysis, and this is what we want. We want the steady state short circuit current. 60909 is the steady state analysis, and the 61363 is the transient short circuit. Transient short circuit which find out the short circuit current with respect to the time. For example, at 100 millisecond, 800 millisecond, or 1 second. So this is the difference between 60909 and the 61363. 60909 is the steady state short circuit current. 61363 is the transient short circuit current, which provides short circuit current with respect to the time. At what time what short circuit current is coming. Let us see what is the mean by the transient. What is the mean by the transient word? So I took again the short circuit current and further I classified based on their period. So at the instant of short circuit current, the first is the subtransient period. First, like 2-3 cycles comes under subtransient period. After that, there is a transient period. And after that, we have the steady state period. So we must remember that a fault is a sudden event. So again, I'm taking the same reactance and XYR concept. We must remember that fault is a sudden event, and whenever sudden event occurs, the electrical system requires some time to adopt, and such response is called a transient. This is the definition of transient in the electrical system. Time to adopt and this sudden change we can say as a transient. Transient means that is, and this transient, it lasts for a short time. It lasts for a short time. This time required to adopt a sudden event can be understood as the time constant as well, right? Higher time constant means higher time required to last the transient time of the fault current. Electrical system has mostly inductance and resistive load type load. The inductance L resists changes in the current. Inductance L discharge the stored energy in terms of the exponential decay waveform. So whenever we have higher L by R or X by R ratio, it means higher time is required to decay the transient period. So whenever we need need to decide the short circuit rating of switchgear, we take the steady state period short circuit current rating and we use the 60909. Because transient is not is it is going to last after 3, 4, 5 cycles. So we require the steady state. So ETAP snapshot for short circuit. Like here I took standard. Now I have three options: standard, 60909 and 61363. So what mean by the duty? The three-phase device, this duty called as three-phase device duty. So the three-phase device duty is usually preferred to find out circuit breaker short circuit rating or duty. So when we need to find out the breaker short circuit duty, we'll use this option duty. Just click on the duty. Okay. When we need to find out what is the line to ground, line to line, line to line to ground, and three phase in detail, each one by one. In that case, instead of the duty, click on the 60909. This IC 0909 is to run to know all type of fault, line to ground, line to line to line to line to ground, and line to line to line. So then we will use the 60909. Clear? The limitations of 60909.
Sir, can you run duty for any component?
Duty for
Any component in the ETAP?
yeah. Same.
Yeah.
Same. We have developed. We have done the same things. So this I'm running the duty. Motor 10. I connected some motor. So they are providing the fault. So now I run the duty. Yeah.
So this is a breaker rating. It is 34, 35K. So we have to select 36.
Say again 33. This
33K.
one.
Yeah. So
see, this is your bus bar rating.
Bus bar rating, yeah.
So now actually I took fault on both bus. Okay. So let me do duty run again. So here 26.5. So from now I'm taking the fault on this bus. Fault is happening here. This is my fault locations. So grid have 25 kiloampere fault current, 11 kilo voltage. Grid is connected to the HV side of the transformer. So for this entire circuit, I will take 25 kiloampere.
Yeah.
Or I can take, let us see this as well. Let us see this as well. I just click and fault and then see. How much? 0.229,
Yes.
0.3 kiloampere, right?
Yes, sir.
So from here till here, I can take breaker with 25 kiloampere rating.
Yeah, HT side.
And my bus bar rating, I can take 25 or 0.2, which is very close. So I can go with 27 or 30K bus bar rating I can take. Breaker rating, I can take 25 kiloampere. Okay.
Yeah.
25 coming here, 0.229, 0.3 coming here, 0.3 in this circuit, 0.3. But since this is connected to the HV side, so I'm taking 25 for this as well. When it comes to the LV side of the transformer, so this side I'm getting 26.5. Right now, so I can take 26.5 kiloampere breaker rating.
Okay.
Here, bus bar I should take 35 kiloampere. This side, yes, if I take any MCCB which is 10 kiloampere, that would also enough.
Okay.
Which is connecting to a 800 kVA. So if I'm taking any 10 kiloampere, that will also enough.
Fine, sir. Thanks.
So this is how I can get the duty of breaker rating. Same thing, same result I will get if I run 60909. Here go and take three phase. Run again. Same you will get.
Yeah, 20 basis.
So taking this, I'm telling that three phase device duty is usually preferred to find out the breaker short circuit rating or duty. 60909 is used to be run to know all the type of fault line to ground, blah blah blah, line to line, this. Okay, so I hope I'm clear with this.
Yes, sir.
I'm clear with this three options. Duty 909-61363 as well, right? I use all the three options. Okay, so there is some limitations of 60909. I hope Venkatesh will discuss all the limitations. There is some exceptions of 60909. All I think that also Venkatesh will discuss. So I'm not going in that, assuming that Venkatesh is going to discuss all these things. C factor, voltage factor, Venkatesh, I think they have discussed yesterday about the C factor, voltage factor, right? So assuming that they will discuss about this all. Okay. So is it okay if we close now and remaining you all proceed with the Venkatesh?
Yes, sir. Sir, there was a one discussion whether the motor acceleration will be taken in this class, the TAP.
Actually, as per the syllabus, it is not.
It is not, sir, but we request if time permits at least
Oh.
one session.
I will also request Venkatesh to.
Yeah.
Actually, I have requested already to deliver the arc flash. Okay. Which is also not part of the syllabus, but
Yeah.
that they accepted that they will deliver the arc flash. I will try for the motor acceleration analysis.
Yes, if time permits, sir.
Yeah.
Thanks.
Okay.
So one question, sir. So in hello, sir.
Yeah. Say yes.
Sir, in SKM, will we get the better results regarding short circuit calculations, or we will get the same results as ETAP?
To be honest, I'm actually mostly I have used the ETAP for the industrial electrical analysis. I use the ETAP. I have not compared both the SKM and the ETAP, but what I can say, both they are following the 60909. So the result should be come around similar. There might be some small variations due to the C factors or due to the other factors, but there would not be drastically change between the SKM and the ETAP. Because both these softwares are utilizing the electrical standards. They are not having their own algorithm for the calculations. Just we do not want to do all the iterations and calculations. So for that we are using taking the help.
So,
Sure,
sir,
sir. Thank you, sir.
kindly share the kindly, sir, C factor will be update, sir. Please repeat the C factor, sir.
Yeah, tell me about the C factor. C factor basically the voltage factor, Harshil.
Okay.
I'll come on the C factor.
Oh, it's a little bit. Okay.
Yeah. So here, if you see, for the C factor where we do this, So when you do the short circuit analysis, then you go to the unit study case, short circuit case. Here, go to the standard, and here all comes about the C factors and the standards. So see here. Short circuit current, maximum user defined C factor, minimum excluding duty cycles. C factor 1.05, 1.05, 1.1. 1.1 is the maximum C factor that we take. Why we take this C factor? This C factor basically is the voltage factor. And why we take this voltage factor? The reason behind this, in short circuit current calculations, the C factor is introduced considering when the low voltage, then higher current, if power is fixed. If low voltage, then higher current. If your P is fixed. So the C factor is introduced to take margin due to the lower voltage variations. C factor is defined in table 1 of 60909 standard, is used to calculate the maximum fault current. C factor is given here. You can see I took this extract from the 60909. Why C factor? So voltage variations depending on the time and place, changing of the transformer taps, neglecting loads and capacitance by calculating quantities, the sub-transient behavior of the generator and motors. So to take the margin of this all, we are taking the C factor in the calculations. I'll take one example. for the C factor. What should be the value? I'll come on that, but why C factor? So let us take a power motor which is 200 kilowatt. Herschel, voltage
Yes, sir.
415. And
Yes.
when we have any motor, we have a plus minus 10% voltage variation as well on the terminal, right?
Yes,
That,
sir.
what is the plus minus 10? So this voltage plus minus 10% that motor can tolerate. Power factor of the motor 0.8. Now if we calculate the current would be for this motor would be P divided by root 3 V into cos
Yes.
phi. So my
Yes,
current, now I'm taking the 415 voltage, rated voltage. So my current coming 347.81. Now
Yes.
suppose my terminal voltage is not the 415. There is plus minus 10%, so minus 10%. Taking the same thing, but I'm putting the voltage at the terminal of the motor is 380 voltage.
Okay.
Right? So
Yes.
at that moment, my current coming 380 ampere.
Yes.
Everything is same, but my current drastically changed from 347 to 380. So the difference is 32 ampere,
32
right?
point. Yes.
So 32 ampere difference in your normal current. You think that would be different? There would be difference. Same would be difference in short circuit current as well, right?
Yes, sir.
So
Yes,
what
sir.
I took here, this 10% means I took 1.1 margin.
1. Yes. Yes, sir.
So what I do in here, I'll go. So if in every calculations, I have to multiply by 1.1 every calculations.
Okay, sir. Understood.
Okay. So here I go here, short circuit current. If I took click maximum, so 1.1 you can see, right? IEEE see ETAP automatically changed to 1.1. That I told you, that is the maximum C factor, 1.1. User defined. So if I have any choice, I can define this, what the C factor I want. Right? Minimum I can define it. Maximum is the 1.1. So why C factor? I hope you understood why C factor.
Yes, sir. Yes, sir. Clear, sir.
And what the value of C factor? Go to the 61909 table 1. Here is the value. Low voltage 100 voltage to 1000 voltage. C factor 1.05 or 1.10. Up to 1, up to the 1000. 1 kV to 230 kV 1.1. 230 1. Maximum C factor is 1.1. So
Yes, sir.
Tolerance, you see here, low voltage system with a tolerance of 10%. So here, like this tolerance I'm putting here as a C factor into
Okay, sir.
data.
Understood, sir.
Variations.
Okay, sir. Okay. Understood, sir. Thank you, sir.
Yeah, thank you, sir. Okay, so I'll leave other with the Venkatesh. He will deliver one class, and in that they will take a SLD, and on that SLD he will perform the short circuit current calculations. What I discussed today, I discussed like we have different kind of the electrical system. So where we need to go with the ETAP calculations and where we need to go with the grid regulations, right?
Yes.
Okay. Is it fine? And then I discussed about the basic concept of short circuit analysis, short circuit current again. Okay, so now coming to the Q&A, let us discuss what the query and doubt. Anything? Anyone have any query? Anyone want to discuss with me anything?
No, sir.
No. Okay, so thank you all for your patience. Thank you for attending the session today. Okay.
Okay, thank you. Thank you. Enjoy.
Thanks, sir.
Thank you, sir.
And so on Wednesday, hopefully I will update if we have the session, otherwise on the weekend, but I'll try to arrange on the Wednesday. Just for the 1 hour at least. Okay. Thank you. Thank you so much. Thank you all. Thank you for the joining.